All right, now we go into protocol layers, and this is actually one of the most fundamental lectures in networking. Protocol layers. So listen carefully. Here is the problem. There are two philosophers who want to discuss this problem. Is there a God? Right? Now the problem is that they don't speak the same language though. So there is a problem that they speak the different languages and that they are communicating through a telex system. And now most of you don't know what telex system is, but there used to be a system where you used to just click things, bit, and then they will be received by a telex machine at the other end. So we need three people. We need many people actually. So this philosopher says something, and since he speaks only French and not English, maybe he speaks English and this guy speaks French, that has to be translated into the other language. So we need a translator here, or some common language. Then it has to be telexed. It has to be sent to the other side, and then it has to be received here, then given it to a translator which translates it into French. So we need two things to be done to the message. One is it has to be translated. Second thing, it has to be transmitted. Right? So what we do is we make three layers. We make three protocols. One protocol whose job is simply to translate. And we write another program whose job is simply to transmit and receive. Right? So this problem of discussion between any two people who don't speak the same language and are far away requires three layers. Right? First layer is what we call the application layer. These people, they know philosophy, but they don't know about translation business and they don't know about the transmission business. Then the second layer, they don't know philosophy. They are not the philosophers, but they know translation. And then the third layer, this person, they don't know anything about philosophy or the translation. They just know that if A comes, I send A the other side. How to send the bits and how to receive the bits. So this is a division of work. It is much simpler to do all this if we divide the work into functions that can be handled by one layer. Based upon this, back in 1980s, the networking scientists sat down and said we need 7 layers. And the first layer is called application. Will simply do the application that you want to do, which is file transfer, email, remote login. These are all applications. Second layer is presentation, and this somehow understand that whether it is an ASCII file or a sound file or a video file or whatever it is, so it knows when the message comes in whether to present it on a TV or write a text on the screen, what to do with this, right? So the presentation layer simply presents the message. Session layer establishes the connection. Transport layer manages the end-to-end communication, and it will become more clear when we go to TCP. The network layer simply does the routing, and the data link layer only uses one half. So data link layer only sends from one computer to the next computer which is directly connected. The routing layer do actually more than one computer. So if you want to go from here to there, first the data link layer will send it here, and then routing will decide that it has to go that way, and then data link layer will send there, and the routing has to decide that it has to go that way. So there is routing layer and the data link layer. Data link layer is two-party, the routing is for the whole network. And then the physical layer. Physical layer does nothing except sending bits. It knows that for a 0 I have to send a transition down, for a 1 I have to send a transition up. So that's the only thing it does. When it gets a set of bits, the physical layer decides how to send those bits. Alright? This is called ISO. What is ISO? International Standards Organization. Alright. So just like ISO is United Nations part, actually it's part of United Nations, but that is for standards. Every country comes to ISO and says this is what we want to make a standard. And then if it becomes agreed, then it becomes the ISO standard. So it's like, you know, UN making saying that, okay, we all should go to Libya or something like that. Similarly, in ISO, we decide as to how the bits should go. All right? So ISO is the organization, International Standards Organization, and they have many, many things, but this is the reference model. It's called OSI, Open System Interconnection. Open System Interconnection, because previous to this, there were many, many systems which were closed, such as we work for digital, I worked for digital equipment, we had our system, IBM had their system, Xerox had their system, Apple had their system, everybody had their own systems. So when OSI came about, this was supposed to be open, that means everybody will use it. All right? And that has 7 layers. All right? Each layer had its job. It turns out that just too many layers. We don't need 7. And so in practice, you need only 3, 4, or 5. And so these 2 layers are generally combined. Data link and physical are combined. The network and transport are generally very much related. And then session, presentation, and applications are combined. But before we get into that detail, there are 2 more terms about the ISO OSI model that we might need later on in this course. And I want to emphasize them because they're not very well described in the book. First is the session and protocol data units. So when a transport layer talks to the transport layer, they use a message between them which is called protocol data unit, PDU. And so there is a transport PDU, there is a network PDU, there is a data link PDU, and there is an application PDU. So when one layer talks to the other layer, that is called a PDU, right? When same level at the other side. When the higher layer talks to the lower layer, that is called the SDU. So whatever the transport gets from the application layer is called transport service data unit. Whatever network gets from the transport is called network service data unit, NSDU, TSDU, and so on and so forth. This would be TPDU, NPDU, and so on and so forth. And these are all service access points. So when you talk to the lower layer, you talk to a service access point. So there is a transport service access point. All right. So now we introduce 3 terms: access points, service data units, and protocol data units. Service data units flow downwards or upwards. So this is SDU coming down, and PDUs flow horizontal, and so on and so forth. Right? So here is the full detail. Anything that is coming from the application to the presentation is called PSDU, Presentation Service Data Unit. Something that flows from presentation to the session is called SSDU, Session Service Data Unit. This is Transport Service Data Unit, Network Service Data Unit, Data Link Service Data Unit, File Layer Service Data Unit. Things which go in horizontal direction between the application, that is called APDU, PPDU is Presentation Protocol Data Unit, Session Protocol Data Unit, Transport Protocol Data Unit, and so on and so forth. And when the request comes in, then they have another term. So the higher layer will make a request to the lower layer, that will go to the other side, and then the other side will make a request to the higher layer. So this is called the request, and this is called the indication. 1 is the request, and 2 is the indication. 3 is the response, and 4 is called the confirm. Okay? So you could have unconfirmed service. If you have unconfirmed service, then this doesn't happen. You just make a request and indication. All right, TCP/IP which is the protocol that we use today, was done before ISO OSI. ISO OSI was done in 1984. TCP/IP was done in 1974, 10 years earlier. And in 1974, as I said before, 1984, there were lots of protocols. Digital had its own, and I said IBM had its own, and the universities had their own, which was TCP/IP. And so we in the industry really didn't care for TCP/IP that much, because this was a non-standard researchy thing. And we were working on OSI model, ISO OSI. But suddenly something happened, and now the whole OSI thing is gone away, and only thing left is TCP/IP. All right? So TCP/IP did not follow the OSI model because it was before that, before OSI model. However, after the OSI model was developed, TCP people said, no, we have layers too. We have layers too, and here is our layer model. So here is their layer model, which we'll talk about, but it's not very clean because they did not know about the layers when they designed it. TCP/IP was made public by NSF, and so there is a whole history there as to why it became famous. But anyway, so this is what it is. The TCP/IP, and when they designed TCP/IP, they did have applications which ran either on TCP or UDP, and TCP and UDP run on IP, and IP runs on Ethernet or point-to-point or packet radio, which run on coax or fiber or wireless. So this could be called the physical layer. This used to be called host to network layer, which can be similar to the data link layer. This is called internet protocol, that can be called the network layer. This is the transport layer, and then the application layer. So there is maximum of 5 layers. There is no session, there is no presentation. All right? And not only that, these are not really layers. TCP/IP are very much like this. You cannot separate them. You cannot run TCP on any other network protocol. So they are not layer. Layer means that you could change the layer below and things will still work. All right? But having said that, this is it. Basically, this has survived. And so in the rest of this lecture, this class, we will teach you about TCP, we will teach about UDP, we will teach about IP, FTP, and so on and so forth. All of these things. And we'll call them layers, but they are not very clean layers. Okay? All right. Now, this particular book that we are using in this course follows a special model, which means top-down. It says somewhere top-down approach. So we start with the application layers, and then we move to transport layer, then we move to IP layer, then we move to the lower layers, and so on and so forth. There are other books that we have used in the past that go bottom up. That will do the physical layer first, then data link layer. There are third set of books that really don't follow any of this, and they hold different approach. So anyway, so every author, every book has its own approach. We will follow the top-down. So how the OSI and TCP match? Well, OSI says application layer, which is actually not complete application. It is application plus half of the session. When they say TCP, the transport layer, it has half of the session and the OSI transport layer. When they say IP, it is not complete network layer. It has part of the network layer, and then part of it goes into what we call the access here and the data link. So there is no one-to-one match with OSI, and it doesn't really matter now because there is no OSI. But sometimes we use the OSI terms. For example, we say layer 3. It's very common for people to say layer 3. So what is layer 3? Well, by layer 3 we means IP. Sometimes we say layer 4, we mean TCP. Even though this is somewhere between 4 and 5, we say layer 4, we mean TCP. We say layer 7. Now, there is no 7th layer here, but in TCP/IP, if we are sitting in a meeting and we say layer 7, we mean application, period. Okay, which is this layer 7. This is layer 7. Could be called layer 5 as well, but we don't call it layer 5, we call it layer 7. So you know how layer 7 came about. You can't clearly say, well, there are not 7 layers, but this is layer 7 because OSI had it at 7th layer. This is layer 3 because OSI had it at layer 3. All right, in fact, we use the term L2, L3, L7. L2 is layer 2, L3 is layer 3, so on. So OSI introduced the concept of services, interface, and protocols. They were force-fitted to TCP later. It's not easy to replace protocols in TCP. So TCP, as I said, TCP and IP are very much merged. When we make a TCP packet, we put the IP header in it first. So you cannot run TCP on any other protocol. In OSI reference model was done before the protocols, and in the TCP world, protocols were done before the models. In TCP world, when it was designed, the design principle was implemented. If it works, then we make it a standard. In the standards world, they make it a standard first and then you implement it. Okay? So that's a different philosophy. OSI, standardize first, build later. In TCP, build first, standardize later. So OSI took too long to standardize. They took 5 to 10 years to write a standard by the time people said forget it. Okay? So then it never happened. TCP was already in use by that time. OSI became too complex. TCP is not general, but it works. So how these layers work? The way these layers work is that you take the user data. Let's say you want to send a message, I believe in God, right? That's the user data. You put a TCP header on it, so you put some more bytes in front of it. Then you give it to the IP. IP puts some IP header in front of it. Then you give it to the Ethernet or any other subnetwork that you're using, and that puts header in front of it. So when you see, if you see the packet on the wire, it has the subnetwork header, then it has the IP header, then it has the TCP header, and behind that is the user data. When it goes to the other side, the subnetwork layer reads the header and does whatever the header says and gives it to the IP, removes its header and gives it to the IP, right? And the other side, IP reads the IP header and does whatever it's supposed to do by that header and then gives it to TCP. So TCP only gets this much. Then the TCP reads the TCP header and removes itself and then gives to the user data. So user application only gets the user data and does not know what happened to the packet on the other layers, right? And what was in the header in the other layers, it doesn't know that. All right, so what are the applications? TCP has many applications such as BGP, FTP, STTP, SMTP, Telnet, SNMP. Some of these applications run on TCP, some run on UDP. So there are two transports, and we will talk about both of them when the time comes. So we'll start from here. We'll talk top down we are going. So we'll talk about these applications first, then we'll talk about TCP and UDP. Then we'll come to IP and down. Now, in addition to IP, there are some protocols here in TCP IP protocol stack called ICMP, IGMP, OSPF, RSVP, etc., etc. They don't really fit very well, but they are required for operations, so we'll talk about them as they come. Anyway, so the idea is that there is a layers, and that there are headers are added at each layer, and then the packets go to the other side, and then the headers are taken off. So we are going to finish this chapter. So the thing is about security. We are going to talk about different aspects of security, so let's get on to that. First is, when we say security, we mean three things. CIA. If you want to remember what do we do in security, we remember CIA. CIA stands for confidentiality, integrity, and availability. We want to make sure that nobody can read. Confidentiality means that nobody can read our data. Integrity means that nobody can change the data. Suppose somebody can read it. That's not a problem, but I don't want anybody to change it. Right? It's like your homework. When you submit it, you probably, confidentiality is not there, but you want to make sure that nobody changes the homework before it gets graded, right? Then you need integrity. Availability means that people who are supposed to get it, and other people don't. So, for example, if somebody does a DOS attack, we call it denial of service attack, where you send so many requests to a computer, to a server, that really the people who are supposed to get it, use the server, cannot use it, and server is totally overloaded. So that is called denial of applicability. That is called unavailability. So you combine all these things and you get CIA. Next thing to know about is what are the bad things that can happen to your computer. So first is the virus. What is a virus? Virus is a code that attaches itself to programs, disk, or memory to propagate itself. So the virus is something that is a method of how it propagates. It can attach to a disk, and when you put the disk on the next computer, it can appear there. It can attach to a program. When you run the program on the next computer, it can appear there, or it can be on the memory. On the other hand, worms are different. Worms install itself on another machine by finding username and password. So they travel by network, right? So if you have 5 computers and you use the same username and password on those 5 computers, a worm will know that your username is this, password this. It will try it on the other computer, and if it succeeds, it will move. Okay? Trojan horse. Now, everybody knows the story of Trojan horse. Basically, that's a Roman war. In the Roman war, what happened was that when the army could not get into the fort, they made a toy horse. A horse which was made of wood, and it looked like something for entertainment, and they brought it inside the fort, and then the whole army of people came out of that wooden horse. That is called a Trojan horse. A Trojan horse is something that comes out as an entertainment, but really, kills the people inside, right? So it's like you download something from the internet. It looks like something useful to you. It might say a movie name, or it might say something else, or some utility which is useful to you. But when you execute it, it infects your computer. That is a Trojan horse. Trojan horse pretends to be utility and convinces users to install it on their PC, but when you install it, it just, it's bad. Spyware is something that collects data about you and sends it to somebody else. So it's not a virus, it's a spyware, because they know what you are buying, what you are selling. So here is an interesting exercise you can do. Go to Google, do a search on some topic. Let's say you do a search on mortgage rates. Next day, count how many emails you get about mortgage offers. You'll be surprised. Everything that you are doing is being monitored. Somebody is monitoring that you're looking for mortgage rate, so all the banks will start sending you this thing. Do a search on shipping or something, and then you get a message all about shipping. Do a search on pool, and then you get a message about pool. So that is spyware. There are programs on your computer which monitor every activity that you do, and then they tell somebody that, okay, this guy is searching for this, and then they make use of that. Hoax. They use, so they will say, well, here's the last bit. If you just send this message to all 100 people, you will, get this and that, and the guy will be cured. And there may not be a guy at all. There may not be a child at all, but that is just to collect a lot of information. Trapdoor. Trapdoor is slightly different. It's something that the developers of the software put. So you might download an FTP program or something else. It doesn't matter, and they might have a way of getting into that program from anywhere. So, for example, simple example is I have a DSL modem, and so I called the DSL company that I have a problem with this modem. They said, okay, let me log into your DSL modem. So they were able to log into my DSL modem and see everything without anything. So they have a trapdoor, right? And if they wanted to, they could probably monitor every bit that I'm sending, on the net. Logic bomb. Logic bomb is an instruction that triggers on some event in the future. So it's a time bomb where they say, okay, on day 1st January 2000 or whatever, something was supposed to happen. Nothing really happened actually, but people could put a time logic bomb where on a particular date and time things will happen. A zombie is an instruction that can be triggered remotely. So this is something that can be done, is that once the virus is on your computer, one form of virus is a remote control. Basically, the people somewhere else can send something to that program and will do whatever they say. They might say, please send a request to Amazon. If they send it to 100 computers, or if they send it to 10,000 computers, 10,000 requests will be sent to Amazon. Amazon will be busy resolving those requests, and nothing will. Basically, this is a kind of denial of service attack. This is also called a botnet. A botnet is where there are computers that can be controlled remotely by bad guys. Okay, so zombie. So anyway, so what happens is this can also be used for other kinds of attacks. For example, a zombie could be ordered to send an email. So your computer could send out, for example, once I got infected, my computer was asked to send out 1,000 emails to all my people on my list, and email of some kind, but I don't know what the email was, but I did get a message from the support saying that your computer is just going crazy, it is sending out so many emails. And then we had to find the problem and fix it. Right? So these are all different kinds of malware that we talk about in the security course, and we talk about how to get rid of them. We talk about types of attacks. So denial of service is one attack, which we talked about, flooding. Buffer overflow. So one way they can get into your computer is by causing a buffer overflow. And what happens with the buffer overflow is that if when your program, when you write a program, generally you put the things on the stack, and then you come back to the stack and return from a procedure call and all that, right? But if there is a buffer overflow, the computer doesn't know where to go. And in that case, they can program it so that it goes into their program, which is a bad virus or something like that, and gets executed. So that is the buffer overflow method. Malware, we already talked about. Brute force is that you can try all the passwords. For example, this week's homework for my network security people is to hack into our server and to find their password. So such things exist, right? Port scanning is that they want to find out what are the applications that are running on your computer, such as FTP server or web server, and then use them. Network mapping, trying to find out what computers are on your network. So all of these things can be done. One way to attack a computer is to cause a buffer overflow. So one can write a program that will purposely cause a buffer overflow. When the buffer overflow happens, the stack overflows, and the routines will not find the proper return address, and they might end up at a place where the hacker has put his program, and so some code will be executed that was not meant to be executed. So that is one of the methods of causing these attacks. Another method is what we call distributed DOS attack. DOS is denial of service. Basically, what people do is they distribute their programs free over the internet, and those programs have viruses in them. And once they have virus, once they're installed on your computer they can control from their computer. And so this is called what we call botnet. Botnet, B-O-T, botnet. So they sell the services for the botnet, then people buy those services, and so advertisers buy services, for example, and using botnet, they can have the computers do anything, including sending email, attacking a computer, attacking a website, and whatnot. So basically, a denial of service attack happens when millions of computers suddenly send requests to one server. That server gets overflooded, the site comes down. It could be Facebook, it could be YouTube, it could be Amazon, whatever, right? And so that thing happens. In fact, there is a program called Trino that you can download somewhere on the internet, and that basically allows you to do this kind of attack. There is another program which allows you to do this kind of attack. So anyway, so these are all the things that we talked in more detail in network security class.